Hello, my name is Luis Ángel Ruiz. I'm professor and researcher at the Environmental Cartography and Remote Sensing Group of the Polytechnic University of Valencia in Spain. In this video, I will introduce synthetic aperture radar systems. First, we will describe radar sensors, its components, and the working principles of side-looking airborne systems. Then, we will see the influence of the wavelength and polarization of the system, and the radiometry of SAR images. And finally, we'll introduce the Sentinel-1 mission from the Copernicus program. In the electromagnetic spectrum, microwave region ranges from wavelengths of about 1 millimeter to 1 meter. This region is located in an atmospheric window. There are two main types of microwave sensors: passive, those that don't emit energy themselves, but are sensitive to the naturally emitted and reflected energy, and active sensors, which are able to emit and receive energy, so they don't depend on external radiation sources. The term radar, radio detection and ranging, is used for all active microwave sensors. A typical radar system is composed of a transmitter, a receiver, a duplexer to switch the signal direction between transmit and receive, a control unit, and an antenna, which is used for both transmitting and receiving. Because of their active condition, radar system can work day and night. The side-looking radar is the most common system for image acquisition. The radar artificially generates pulses of microwave radiation and sends them perpendicularly to the flight line, illuminating narrow strips on the ground. The backscatter energy is received, amplified, and analyzed to determine location, electrical properties, and surface configuration of the objects. Thus, echoes from the objects situated closer to the ground track are received earlier. In this manner, target signals are converted into time amplitude signals. After the last echo is received, which is determined by the swath width, a new pulse is emitted. This table shows the wavelength and frequency intervals of the principal radio spectral bands, which they are commonly referred by letters from K to P, in increasing wavelength. The radar return is directly related to the wavelength at which it operates. Wavelength governs whether a surface behaves as rough or smooth. In addition, the larger is the wavelength, the deeper can penetrate the signal, carrying some information about the underground, as we can see in this comparative example of an image of the visible on the left and a radar image on the right. Electromagnetic radiation propagates orthogonally to the electric and magnetic fields. The polarization components of a system is defined by the plane of vibration of the electric field, and it be horizontal or vertical. There are four basic types of radar polarization. Two like polarized, horizontal-horizontal and vertical-vertical, with equal polarization plane at the emission and at the reception, and two cross-polarized, horizontal-vertical and vertical-horizontal with different polarization planes. The like polarization increases the signal-to-noise ratio, resulting in images with less noise. The cross-polarized systems measure the depolarization component of the signal, which is due to the corner reflectors, surface roughness, or volume scattering. The most common types of radiometric response in a radar image are specular reflection, hard reflectors, corner reflectors, and diffuse scattering. Specular reflection is produced by smooth surfaces, where the angle of reflection is similar to the angle of incidence. This effect is used in applications such as spill detection, where the smoother surface of the oil increases the specular reflection component, so the energy is reflected out of the scope of the system, and the oil slick appears darker in the image. Here we see a similar application in the ocean, where the wake of a ship is quite evident due to the specular reflection of the oil slick left by the ship. Another application of SAR images based on the effect of specular reflection is the detection of mapping of floods. In these cases, the flooded area is detected due to the lower level of backscattered energy reaching the sensor. A great advantage of SAR images is that they are not affected by clouds and rain. After flood detection, the affected area can be mapped and crossed with high-resolution ortho images or land-use land-cover maps in order to quickly assess economic losses. This is, for instance, a similar product to the ones delivered by the Emergency Management Service of Copernicus program. The effect of corner reflectors is produced by objects with rectangular shapes. The vertical walls combine with the horizontal ground that produce echoes with very high returns. This is the case of buildings, sharp hills, and other similar objects. Here we can see two examples, one of them showing a typical urban landscape, another showing an ice jam where the edges of ice blocks act as corner reflectors. Usually, metallic objects produce very strong responses due to their high dielectric constant, and they are called hard reflectors. Examples of those are metal bridges, railway tracks, ships, or metallic towers, as shown in these pictures. Finally, diffuse scattering is characteristics of rough surfaces and vegetation, because the leaves, twigs, and branches create an heterogeneous structure where multiple volume scattering is produced, generating an intermediate or high radar return. The first Sentinel-1 satellite was launched in April 2014, the second in 2016, and discontinued in 2022. The satellites of this Copernicus mission follow asynchronous orbits with 12 days of repeating cycle each, working in band C and providing images with single light polarization or dual polarization. One of the most used correction levels is ground range detected, GRD, where images are provided at about 10 meter spatial resolution. And with this, we finish this brief introduction to SAR systems. You can go deeper in this topic consulting complementary materials. Thank you for your attention.